doesn't seem really as simple, and I can't help but stare, 'cause I see truth.
So, I told you we were going to start podcasting, and I think today is the day that we are thinking about. Yeah! Alright. So I think anytime this little thing is blinking, I think we're going live. It seemed to work well with the 10 o'clock. Alright, so funny thing about that. So I talked to some other professors who have done similar sorts of things, and they're like, yeah, it's really easy. Software's already on here. You're just going to make sure you get a mic. And so the mic that other people have, you know, they've got just USB plug-and-play mics. Really easy. You just bring it in, plug it, you're good to go. And so I looked for, you know, I read some reviews, looked at maybe what the best plug-and-play mics were within a reasonable price range. Had the department order one on Amazon. And so it comes in the mail, and I mean, so the mic that Professor Abel uses, I think, is about, I mean, it's like plastic, and it's like that tall, right? It's not very big. And so, to my surprise, the mic that comes in the mail is this thing. And so this thing weighs like 5 pounds. And so I think it's gonna work fine. As we go, it worked in the 10 o'clock section, but I was showing some people in the department, they had lots of jokes about overcompensating with something, and I don't even know what that means. So whatever they're talking about with their jokes, that's kind of what I've been living with the last couple of days. Okay, so my wife and I went out to dinner last night, and we were driving home, and she's like, is there a bush growing in our yard? Like in our front yard where our steps are. I was like, I don't think so. I don't think those just like spring up overnight. And so we were like, we should walk around, because we don't use the front door. We're backdoor people. And so we went around front to check, and it was our Christmas tree. And so like in January, we were like, oh, we better get this Christmas tree out of here. We just threw it out the front door, and apparently we are just the trashiest people now, because there's just an old Christmas tree sitting in our front yard, and basically we just lack like a Trump sign, and we fit in perfectly well with the part of Virginia where I grew up. So I figure that's about as safe as I can politically go. I'm not going to offend too many people with Trump. So okay. Some of you I might have. I'm sorry. That's as far as we'll go politically. All right. So let's see. Anything else? All right, so we're good until after spring break. Exams done. We don't have to worry about homework until the Friday after spring break, I think it's due. So we can pretty much relax and spend the next few weeks, well, at least maybe the next week, kind of doing some chemistry stuff, and then the week after doing everything possible to get away from chemistry for at least a week or so. All right, so the exams, they're being graded. And so I usually wait until after the first exam to have this talk. If you've had me in class before, you know that I put a lot of emphasis on the final. And so if you walked out of your exam and you were concerned that maybe your grade wasn't going to be where it is, well, first off, relax, because organic grades, again, at least percentage-wise, are lower, but there is usually a substantial curve that comes along in an organic chemistry class. So wait until you get your score back. I'm not going to meet with anybody regarding the exam until after I get them back to you. But my point is that I put a lot of emphasis on the final. And so when it comes to assigning grades, I don't care what you got on exam 1 if you nail the final exam. And so basically, I like to see improvement as we go. And so all the options grade-wise are still there for everybody. And so we'll go ahead and plow forward. And furthermore, the exam, how many points were on the exam? 200. How many points are there total for the semester? Everyone reads their syllabus. 1160. And so that comes out to about 17% of the final grade. And so this isn't like a 35% midterm. This is a relatively minor midterm as far as it can count towards your grade. So just wanted to make sure everyone could go into the weekend feeling a little bit better, maybe about how the exam went. All right, so last time I think we were sneaking into the notes that there were some rules that we're going to talk about when we start prioritizing groups so that we can name the stereochemistry. And so so we talked about assigning priority. And so ultimately what that allows us to do is number and then rank the substituents, and we can then classify our stereoisomers with whatever designation is appropriate in that case. All right, so there's 3 rules, and all of the rules pretty much have to do with atomic weight, and so that makes it pretty easy to is that rule number 1 is that the higher atomic weight, the higher priority. All right, so it really is that simple, and in a lot of cases, all you have to do is see what's connected, see what's heavier, and then that's how the groups are prioritized. So for example, what we could have is we could have something that looks like this. We'll have an alcohol, a hydrogen, an amine, and then we'll just put a methyl group. Okay, so could we use cis-trans to name this double bond? No, because to name them cis-trans, we'd have to have both a hydrogen connected on the left side as well as a hydrogen connected on the right side. And so in this case, we've got the hydrogen on the left side, but we don't have the hydrogen on the right side. All right, so what we've got to do is we've got to prioritize our groups. And so in doing so, we look at that left side. All right, so we've got an alcohol on going up and then a hydrogen going down. And so that first point of connection, we've got an oxygen on the top. And then we've got a hydrogen on the bottom. And so what has the higher atomic mass? Oxygen or hydrogen? Who gets the higher priority? Oxygen. And so we would say here, we're going to get that priority number 1. And then down here, that's going to get priority number 2. I cannot find my laser. Right here. Hold on. Okay, so we've got our priorities assigned. Then we look to the right side. All right, so we've got 2 different groups attached to our carbon. One is an amine with NH2, and one is a methyl group CH3. And so at that first point of attachment, we have a nitrogen and a carbon that we're comparing. And so which has a higher atomic mass? Nitrogen, right? It's further on the periodic table than carbon. And so what's our priority number 1? It is the nitrogen. Okay, so we've prioritized our groups. And so now what we can do is we can finally give it that EZ designation. And so in this case, our higher priority group is on the same side. And so do we name that E or Z? We name that Z. All right, so we talked about the difference between E and Z last time. Okay, so if we've got different groups, it's pretty easy. We just compare them and we pick the higher one. All right, so then if that doesn't work, we roll to rule number 2. So we can say that if rule number 1 doesn't work, we want to use the first point of difference to be our decider. All right, so what does that mean? So we'll draw an example, and so in this example, we'll say that we've got a bromine on the right top, a hydrogen on the bottom right side, and then on the left side, we'll put a methyl group, and then put an ethyl group on this side. And so what I'll often do is I'll redraw this thing out showing all the bonds that are being made, and that way it can be a little easier sometimes to see where our first difference is. And so if we redraw this thing, we know that we've got a molecule. The right side stays the same. It's nice and simple, just a bromine and a hydrogen. Now let's go ahead and give that priority. Which is higher priority, bromine or hydrogen? Definitely bromine, and so we'll give that a 1. Hydrogen gets a 2. And in general, whenever you see a hydrogen, it's going to be the lower priority group. That's just something you can remember, right? Hydrogen's number 1 on the periodic table. There's nothing that has a lower mass than hydrogen, and so almost every time, I can't think of a case where it wouldn't be your lowest priority group. Yeah. If there are 2 hydrogens, then we're going to find there's not always stereochemistry. There probably might not be a designation to be made, right? We talked about a terminal alkene last time where one of these carbons would have 2 hydrogens, and so we just say there's no stereochemistry because there's no difference to be made. All right, so on the left side, let's draw our atoms out. So we've got our methyl group here, and then going down, we've got our ethyl group, so we've got 2 hydrogens, and then of course an additional methyl group attached to those. Okay, so we count to our first point of difference, and we find here that's a carbon, and so that's a carbon. Is there any way to tell the difference between those two just based on that? There shouldn't be, right? It's the same atom, and so what we can say is that, well, the heaviest thing connected to this carbon, the heaviest atom, what is it? It's a carbon, right? It's this right here. And we never want to count back towards the double bond. We're always going to count away from the double bond. And so we look at this carbon and we say, well, it's connected to one carbon and two hydrogens. Up here, this carbon, what's the heaviest thing it's connected to? It's a hydrogen. And so which group do you think gets priority, the top one or the bottom one? The bottom one, right? So the first point of difference we would say is, let's say right here versus right here. And so since the bottom group is bigger, we give the bottom groups a priority. Okay. That's pretty much the rules, yeah.
So with this double bond, do we only go up to 2?
That's the perfect segue into rule number 3, where we deal with pi bonds. All right, so rule number 3, there's going to be situations where there might be pi bonds on our structure, and so what we will say is that pi bonds count as extra copies of bonded atom. All right, so yeah. Yeah, those are switched. So the ethyl group on the bottom is definitely higher priority than the methyl group. And so if we gave that molecule an EZ designation, what would we call it? We would call it E. So now our higher priority groups are on different sides of our double bond, and there's no bond rotation in a double bond, so we would say that that is E. All right, so I got a new model kit, so I even brought these to show. So I used purple for pi bond, right? And so what we've got is we've got this double bond, and so on top we can see there's overlap from a pi bond, and the bottom it's the same pi bond, right? Because we've got two p orbitals, one on this side and one on this side. And so if we try to rotate this thing, you'll see that ultimately that purple would have to fly off or break. There's just no bond rotation in this because we no longer can have that connectivity between the top of these p orbitals if we start to rotate. So if we go down, it just doesn't work. So that's why we don't have, or at least, the reason we don't have bond rotation in these things, and so that's why we have stereochemistry at all. All right, so pi bonds count as extra copies of bonded atoms, and so our example for that, a methyl and a hydrogen, and so without even having to think about this, on the left side, what's the higher priority group? It's the methyl, and then we've got the hydrogen on the bottom. So then on the right side, we'll use this as our two examples. Okay, so we break our group right here. To the top right, when we have a single bond meeting a triple bond, how many carbons are there in this substituent? There are 2. And so at this interface there is a carbon, and at that interface there is a carbon. Okay, so we've got 2 carbons on the top right, and so when we redraw it, here's what we're going to do. So here's our first carbon, so we'll call that C1, and that's carbon 2. Now, carbon 1, as we go right from our connection, carbon 1 is connected to how many atoms? Just 1, right? It's triple bonded to carbon number 2. And so what we're going to do is we're going to treat that as if carbon number 1 is bound to 3 different copies of carbon number 2, right? So it's basically just going to be 3 times 1. And so when we draw it out, what we'll say is that, well, here, here, and here are all copies of carbon number 2. All right, so essentially what we've got is carbon number 1 is connected to carbon number 2 3 times, and so when we redraw this out, we're actually just going to show 3 different pictures of carbon number 2, indicating each of those bonds that carbon number 1 is making to carbon number 2. All right, so then carbon number 2 is connected to how many things? Well, it's got the hydrogen to the right, but then it's also connected to that carbon on the left. And so we're already showing it bonded once to the carbon on the left, and so we need to show 2 more times that connection. And so we'd say, well, just draw in carbon number 1, and now carbon number 2 is connected 3 times to carbon number 1. And that's just so when we look at this, we'll see the 3 different things that it can possibly be connected to. And then to the top right, it's connected to what? That's just our hydrogen. All right, so then we've got an isopropyl group on the bottom right, and so essentially what that looks like, we have a hydrogen and then 2 methyls that are connected to our point of attachment. So we've got C, CH3, CH, and then yet again another CH3. All right, so following rule number 1, our first point of attachment, right here it's a carbon, right here it's a carbon. Does that help us out at all? It does not. And so then what we have to do is we have to go to the next point of attachment. So looking at this carbon right here, what's the heaviest atom it's attached to? It's a carbon. What's the heaviest atom this is attached to? All right, so we forget that first, basically the heaviest thing's there. What's the second heaviest thing that's connected to? It's a carbon. What about here? Carbon, right? So if we call this the first one and this the second one, we could also call this the first and second. And so ultimately we have to go to the third attachment. So what is the third attachment atom that it's connected to here? Yet another carbon. What about this one? It's a hydrogen. Which one's heavier, a carbon or a hydrogen? It's a carbon. Which is the higher priority group, top or bottom? Definitely the top. And so ultimately we just count away until we find points of difference. And so we would call this one number 1 and this one number 2. Okay. All right, so that's how we're going to apply, or basically assign our priorities of groups. And now that we can do that, we're going to look at the different stereochemistries that we can have, and we're going to learn how we can assign a designation for each. Before we go to that part, we're going to talk a little bit about chirality. And so this is going to be Roman numeral number 3. The title is chirality, and so our theme song today was mirror. And so mirror is going to have a really important role when we talk about chirality. So what we'll say is that letter A, there are 2 types of objects as far as chirality is concerned. And so the first kind are going to be achiral. All right, so just the word chiral with an A in front, we pronounce it achiral. And so an achiral object, we will say, is an object that is superimposable with its mirror image. Or, to even simplify that further, we'd say it is an object that is identical to its mirror image. So basically, we're going to take an object, we think about what it would look like through a mirror, and then if they are the same thing, we've got an achiral object. And it's not just molecules, it's things in life. And so our first example that we're going to use of an achiral object is we're going to meet Mr. Smiley. All right, so Mr. Smiley looks sort of like this, and he's a beautiful, beautiful man. And so Mr. Smiley, what he's got is this perfectly symmetrical face, right? Symmetry, beauty, apparently that's what they hear. I've never come close to symmetrical in my life, so I've never worried about it. So what we're going to do is we're going to imagine every morning Mr. Smiley wakes up. I guess he doesn't do his hair, but he gets dressed. And so he looks in the mirror. Wants to make sure that he is as beautiful as always. And so when he looks in the mirror, of course, his right ear, when he looks in the mirror, looks like which ear? It looks like his left ear, right? And so if you're writing with your right hand, of course, a mirror image of you is writing with their left hand. Okay, so what Mr. Smiley sees, because he is so beautifully symmetrical, is ultimately the same exact picture. Okay, so Mr. Smiley, he the image that he sees in the mirror, is it identical to the actual image of Mr. Smiley? Yeah, because his left eye became his right eye, but it didn't make a difference because he's pretty much symmetrical right down the middle. All right, so the reason for this is we've got this plane of symmetry straight down the middle, and so ultimately what we've got is an object on the right that is the mirror image, but it is perfectly superimposable. If I was a better artist, these would be basically the exact identical images. All right, so when discussing Mr. Smiley's face, would we say that it is chiral or achiral? It is definitely achiral. And the reason that it's like achiral is because of that symmetry. All right, so these two images are achiral, and so what we have are identical images. All right, so we're not as interested in the results from Mr. Smiley, but maybe more in molecules. And so our example today will be this. So what I'm going to do is I've got a couple of molecules, and we're going to see, basically we're going to see if we can superimpose their mirror images. So I'm going to line the blue straight up and to your left. And so for the mirror image, the blue should be straight up and to the right. Now, it takes a little practice. All right, here we go. All right, so here's the thing that you have to keep in mind is when you're doing these mirror images. When you look in the mirror, your nose, okay, so your right hand becomes your left hand, and your left hand becomes your right hand. Does the nose become the back of your head? It does not, and so things with depth are not going to change. So what we've got is we've got this blue to your left, and so it's going to be on the right. Now our green, which is to your right and on a wedge, well, it's going to switch to the left side, just like our right hand becomes our left hand, but it has depth. It's coming towards you. And just like your nose is going out, and then in your mirror image is coming out at you as well, it's on a wedge here. It will also stay on a wedge. And then likewise, our red substituent here, well, if you look in the mirror, can you see the back of your head? You can't. It stays the back of your head. And so this red that is on a dash, it's going to stay on a dash. All right, so what we've got here is we've got a molecule that's looking in the mirror, and it basically sees itself. And the question we want to ask is, are they the same thing? So let's see what happens. What we could do is, let's see if we can superimpose them. So we'll turn this around such that the blues overlap. All right, do the blues overlap? They do, but what about the red and the green? Yeah, so this red is on a wedge and this green is on a dash. So then what we could imagine doing is flipping it over to give us that. Are those the same exact thing? They are. The reason that they're the same exact thing is because we have two substituents that are exactly the same. And so what that does is it allows us to basically show this where the red is in the front, or we could flip it over and the red is in the back. But in both cases, the blues are in the same place. All right, so the key thing here is when we talk about molecules, unless we have 4 different groups connected to a carbon, we're going to have an achiral object. And this is the reason why. It gives us the ability to rotate this thing and ultimately show that it is, in fact, the same molecule. I just got this new model kit. I'm going to have tons of these, so if you guys want to stop in after class and see how, in fact, this is the case, you're more than welcome to. All right, so if we draw this out, the example of a molecule, at least, we would say that, well, we could have a bromine on the top. We put a fluorine to the bottom left. And then we'll have our blue groups, and we'll just say that our blue groups are going to be methyl. So those are identical. All right, so this is very much similar to the molecule we've got here because we've got, say, like a green fluorine and then a red bromine, but then we've got 2 methyls, and we're showing that both of those methyls will be blue. Okay. So if we take the mirror image of this structure, our left becomes our right, but depth doesn't change, and so bromine is still straight up. Our fluorine, which is on the left side, is now on which side? Should now be on the right side. Our methyls, which are on wedges and dashes, are still on wedges and dashes. So if you're shown these 2 molecules and you were asked, well, are these things chiral or achiral? What would you say? They are achiral. And not only would you say that they are achiral, would you say that they are 2 different things? No, they are the same exact thing. They are identical. By being achiral, you are saying that it is the identical object, right? Or that they are identical objects. Okay, so we talked about achiral things, and so basically number 2, we're going to talk about chiral objects. And so as you might have guessed, a chiral object is one that is not identical to its mirror image. All right, so I'll also add that most objects are chiral. Because to be achiral, it requires there to be some form of symmetry, and if we look around the room, most things just aren't perfectly symmetrical. All right, so our example of a big object is, we'll use Mr. Smiley again. So Mr. Smiley decides to see, what would it look like if he wasn't as symmetrical and beautiful. And so what he does is he winks. Just gives himself a little wink in the mirror. All right, so there's Mr. Smiley. He's still handsome. But what he's going to do is he's going to look in the mirror. Now, he's winking with his left eye. All right, and so the image that he sees coming back at him, which eye is winking? Is it the same eye or is it the opposite eye? It is the opposite eye. And so the eye that is now winking is the right eye. Okay, so now we see we have two different images. Are these things identical? They are not identical. We've broken the symmetry by having Mr. Smiley blink into the mirror. And so if we had to say, well, these are chiral or these are achiral, what would we say? They're most certainly chiral. And the reason is that, well, they're mirror images of each other, but they're not superimposable. All right, so they are not identical objects. And so in the chemistry world, of course, we're probably going to do a little bit more with molecules than we are Mr. Smiley. And so I've got examples of chiral molecules. And so let's say, how do we want to orient it? Let's say silver up and blue to the left. And so that means that, let's see, we should have silver up and blue to the right. Okay, now, are these mirror images of each other? Yeah, absolutely. So the blue that's on your left is now on the right when we look in the mirror. Silver stayed in the same place. Green, being on the front, is still in the front, just like your nose. However, it was going to your right here, and so now it's going to your left. And so likewise, the red, which is going back, it has depth, it would be on a dash, is still to your right, and again, is just to your left like the green. Okay, so now that we've got four different groups, let's see what happens. If we bring the silver back towards us, are those the same thing? They are not. Is there anything we can do to make these two things the same? They're not. No matter what we do, we'll never be able to superimpose these things, and the reason is we have a tetrahedral carbon, an sp3 hybridized carbon, bound to four different groups. And so let's say we align blue and silver, we can see that, well, the red and green are going to be swapped. And what you can do is you can align any two of these. Let's say green and silver. And then again, the other two are going to be swapped every time we try to align them. All right, so in this case, we want to write down what it would look like. Let's use, all right, so let's do a molecule. Again, we'll keep bromine on top. Put fluorine to the bottom left. In this case, what we're going to do is we're going to switch one of our methyls to a hydroxyl group. So now we've got OH there. And so when we take the mirror image, the bromine's still up top. The fluorine that was on the left is now on which side? The right. All right, so depth stays the same, and so our hydroxyl group is to the left on a wedge, or I'm sorry, to the right on a wedge, and so now it's going to be to the left, but it's still on that wedge for the same reason that your nose is still on the front side of your mirror image. All right, so on the back, what we'll have is our methyl group, and so when we look at this, we would say, well, these are chiral or achiral? They are most certainly chiral. They are not identical. And as we've seen when we talked about albuterol, and then we talked a little bit about thalidomide, that tends to be a really big deal, especially medicinally when we're putting these molecules into our bodies. And of course, we are chiral, and our bodies react to these things differently. Okay, so that's the idea of chirality. And so we're going to apply this to molecules, of course, and so part B, we're going to label as stereocenters, or chiral centers. And so, what we're typically going to be working with, well, they've got to be sp3 hybridized. typically they're going to be carbons. Now there are cases where you could have a nitrogen that is a chiral center, because is nitrogen ever bonded to 4 different things? Could it be? Yeah. Sure. What kind of charge does it have? It's got a positive charge, and so it's definitely possible, but more often than not, we're talking about a carbon that's bound to 4 different things. So we'll say that typically we have sp3 hybridized carbons connected to 4 different groups. That's what makes it chiral. So in this case, let's say, alright, so we'll have a carbon down here. We'll attach a 6-membered ring to the top side. And then we'll have CH2, CH3. And as we go further, if I draw a CH2, CH3, I might just start abbreviating that as ET. What does that mean? Ethyl, right? It's just a way to even further abbreviate what we're writing. If I ever threw down ET, you know what an ethyl group is, and so you know what's connected is a CH2, CH3. And then let's put a chlorine right here. Okay, so we know our chlorine substituent, our ethyl. What do we call this top substituent? All right, so if it's on its own, if it's just a 6-membered ring, C6H6, what do we call that molecule? It's a benzene. And so that makes you maybe think that this group would be called a benzyl, but it's not. And this is just something you're going to have to remember. This group right here is referred to as a phenyl group. It's super confusing, but we don't refer to that as a benzyl group, because a benzyl group is a different thing. So a benzyl group is where our point of attachment essentially has a CH2 between our 6-membered ring and then the ring or the chain in question. And so if we've just got our 6-membered ring, it is a phenyl group. If we have a CH2 between our 6-membered ring and our point of attachment, that is what we refer to as a benzyl group. I'm not totally sure why that naming system came to be, but it's how it is. And so don't have those things basically swapped. Okay, so if we're going to assign priority to the 4 groups attached to this carbon, well, you see a hydrogen. What's always going to be your lowest priority group? That's that hydrogen. So we'll go ahead and give that number 4. Because unlike with double bonds, where we're basically assigning 1 and 2 on both sides, now we're going to actually assign 1, 2, 3, 4. And so our hydrogen is the lowest. What's our highest? Well, it's not the phenyl ring, because the phenyl ring ultimately is a carbon attached, right? So we're just looking at that first atom. And so in this case, it's actually the chlorine is atom number 17. And so that's going to be our highest. So then we just have to tell the difference between the phenyl group and the ethyl group. And so what's higher priority? Let's think about that. So the phenyl group, this carbon right here, its point of attachment, it's bonded to 1 carbon here. And then going the other way, it's bound to another carbon twice, right? And so we ultimately treat that as it being connected to 3 carbons. This carbon down here is just connected to 1 carbon and 2 hydrogens, and so what's higher priority? Definitely the phenyl. All right, so we call that number 2, and our ethyl group number 3. So we've got 4 different groups. So if we were to look for the mirror image of this thing, we would say, well, our phenyl group is still straight up and down, or at least straight up. Does it matter how we orient the double bonds in this phenyl ring? No. It shouldn't, right? Because, of course, there's resonance going on. So all those bonds are more like a 1.5 bond anyway, so it doesn't matter, yeah?
Wait, how does chlorine, how's it going first priority?
Just because the rule number 1 is we look for the first atom attached, and the higher atomic weight wins out. And so chlorine is heavier than a carbon, or a hydrogen, and so it's number 1.
Okay.
Yep. All right, so then of course hydrogen that was on our left in the plane is now on our right in the plane. Our ethyl group, still on its wedge, but now it's flipped sides. And we've got our chlorine, which is going to flip sides and keep its depth, so it's still on a dash. All right, so when we number these, of course, the priority hasn't changed. Chlorine's still number 1. Hydrogen is still number 4. So when we look at these two molecules, well, are they the same molecule? They're definitely not the same molecule, so they are different molecules, and we know that because there's 4 different groups, so it's a chiral center. And so we're going to refer to this pair. If we talked about the relationship between these two molecules, what would we call them? They are stereoisomers, but we're going to go a little deeper and give them a special name. Starts with an E. So let's put a star in our notebook because we're going to talk about some relationships between stereoisomers where the words are long and it seems really confusing, but we're going to boil it down and make it as simple as possible. So stereoisomers we've defined. We've said those are molecules where we have the same connectivity but different orientation in space. We're going to call these things enantiomers, and then we're going to learn about something called diastereomers down the road. And so there's lots, long-sounding words, but we're going to define them in a way that it should be very easy to remember. So first, if we talk about these two molecules, we would say that they are enantiomers. And so the definition of enantiomers are basically going to be non-superimposable mirror images. Now this might seem obvious based on what we've talked about thus far, but the thing is there's not always just one chiral center in a molecule. And so what we can have is if we have more stereoisomers, and we're going to find that typically for each chiral center, we say that there are 2 to the n possible stereoisomers. So if you have 3 chiral centers in a molecule, how many possible stereoisomers are there? There'd be 8. And so what we're typically going to have is a lot of these other things we call diastereomers. So we're going to see that there are stereoisomers that are quite often not mirror images, but we want to make sure that we know when we talk about enantiomers, we're talking about a pair that are mirror images, but they are not superimposable. And so I'll probably say this a lot, but enantiomers are a very special pair. They always come in pairs because, of course, if they're not superimposable mirror images, there's always going to be 2 of them. And then furthermore, we'll add that they have identical physical and chemical properties. And the reason is, well, they have the same shape, right? It's just they're in reverse. It's the other direction, all right? And we'll talk in a little more detail towards the end of the section, or at least the end of the chapter, more about the relationships between stereoisomers. But I want us to be confident that when we talk about mirror images that are non-superimposable, we can give that the label enantiomers, and enantiomers always come in pairs, a very special pair. All right, so now what we talk about, now that we can prioritize groups, we can actually assign them the specific label that they need to have. And so this section we'll call how to classify stereocenters or chiral centers. And so what were the 2 letters that we used for chiral centers? Yeah, so that's going to be R and S name. Remember, E and Z are only going to apply to alkenes or double bonds. When we talk about stereocenters or chiral centers, we're going to use R, we're going to use S. Okay, so here's how we do this. Number 1, we've already done it. We want to be able to prioritize our substituents. We've learned the rules to do so, and we've seen really all the variability that we'll see in Chem 206 as we're prioritizing. And so we prioritize our substituents. And then what we do for number 2 is we're going to put number 4 in the back. All right, so I'll show you on a model what I mean by in the back. So let's say we've got this stereoisomer. I'm going to take our silver one. I'm going to say that's our lowest priority. I'm going to hide it from you. So basically, now you can see 3 things, right? The silver is on the far side of you. And if we count this alphabetically, what we would say is we'd go blue, green, red. And so let's think about what we're doing when we go blue, green, red. If we put all those in front so that you can see them, if we count blue, green, red, are we going clockwise or counterclockwise? we'd be going clockwise, right? So from your perspective, we've got blue, green, red, and so that's kind of how we're going. Alternatively, the other enantiomer, the other side of our special pair, we'll do the same thing. We'll put the silver behind. In this case, when we count blue, green, red, are we going to go clockwise or counterclockwise? Now we go counterclockwise, right? Blue, green, red. And so that's ultimately how we assign the R or the S when we're talking about our molecules. All right, so let's do the pair that we did above. I'm going to copy and paste this down. All right, so there they are. And so like I said, we want to orient this molecule such that we're looking, and priority number 4 is hidden. It's in the back. And so to do so, in this enantiomer, we're going to look from the opposite side of our hydrogen. So we're going to view our molecule from this direction. And so this kind of look like a half-Newman projection. And so what we'd say is if we're looking from this perspective, the phenyl group, where's it gonna lay or sit? It's in the plane, and then in what direction? Up or down? It's up, and so that's where we'll draw it. We'll say, well, from this perspective of our green eye, that phenyl group is straight up and down. So that's where we put it. All right, so from this perspective, of course, our ethyl group, it's on a wedge, and so a wedge, is that coming towards you or away from you? It's coming towards you, and so if I'm, I guess, going to be the eyeball, so I'm looking kind of from this perspective. It's on a wedge, it's coming towards you. What direction do I look to see you? I look left, and so our ethyl group, which is on a wedge and is also towards you, it is on my what? It is on my left, and so that's where we're going to draw it. All right, so there's the ethyl group on our left, or on my left. So then likewise, the chlorine, which is on a dash, it's going away from you, and so from this perspective, as I look from the right side of the molecule, is it on my right or my left? Definitely on my right. So we draw in our chlorine right there. So basically what we've done is we've shown what our eyeball is seeing from that perspective. Okay, so we know our priorities of our groups. We've got chlorine, number 1, phenyl, number 2, and then ethyl, number 3. And so if we count 1, 2, 3, are we going clockwise or counterclockwise? Most certainly we are going counterclockwise. And so when we count counterclockwise, what we'd say is we have the S enantiomer. All right, so we've taken group number 4, we've hidden it, basically. We've put it in the back. And so what we see, let's make sure we got blue. What we ultimately see is this. And so we're going to count substituent 1, 2, 3. And so we see that as counterclockwise. And so that's going to be S. All right, so alternatively, we can, of course, draw the other enantiomer. And so when we draw the other enantiomer, we keep the same rule. We want to put 4 in the back. We basically want to hide it from ourselves. And so our eyeball will again come from the other side of the hydrogen. So again, we're going to have our carbon in the middle. Our phenyl, what's its direction going to be? Again, just straight up. Now our chlorine is on what? Is it going to be on our eyeballs left or right? Well, the chlorine is going into the back of the board, and I'm looking at it from this side. Is that going to be my left or my right? It should be my left, right? Because it's going away from you, and so I'd have to use my left hand to go out and grab it. All right, so chlorine is to the left, and that leaves the ethyl on the wedge to be on the right. All right, so we prioritize 1, 2, 3, and so now, hold on, wrong way, 2, 3. And so when we count 1, 2, 3, are we going to go clockwise or counterclockwise? Now we're going clockwise, and so what that means is that clockwise, guess which enantiomer we have? We have our R enantiomer. That is the difference between those two things. That's the handedness that we're talking about. So we've got clockwise and we've got counterclockwise when we prioritize. All right, so there's actually 2 ways to do this, and I still basically have some trouble. And so what I do is I use my hand, and I'm going to show you how you can use your hand to maybe simplify this thing a little bit. All right, so we have this way to do it, We can also say a big fat or. And so you can use either your right. Fortunately, we're chiral. I have a right hand and I have a left hand, and that's going to give us basically the tool to figure out if we have the R or the S enantiomer. So, what I'm going to do is I'm going to take one of my hands. I'm going to take the thumb on my hand and I'm going to orient it in the direction of my number 4 substituent. So again, we're making silver the lowest priority substituent, and so I'm going to orient my thumb that direction. And so I want to be able to count blue, green, red, right, in that order. Now my hand. All right, so I know my fingers can curl this way. Can my fingers curl back the other way? They cannot. And so also my hand can only go one direction. So is my hand with the thumb going back towards substituent number 4, is it able to count blue, green, red like that? It is not, right? Because the only thing I could do, I could start at blue, I could curl to red, but there's no way I can go the other direction. However, if I take my left hand, I put my thumb back towards substituent number 4. Will my fingers curl blue, green, red? They will, right? And so I'm using my left hand. And so anytime you use your left hand, you're going to have the S enantiomer. And so what that means is if we're going to count blue, green, red, and we're using our right hand, and this is why I think this is so valuable to remember. All right, can I use my right hand and count blue, green, red? Can I curl in the direction that we're going? Yeah, and so my right hand, which happens to start with the letter R, is what enantiomer? It is the R enantiomer. I find that pretty useful when I'm doing these things, and I'm guessing that you probably will too. And so what you'll be able to do is you don't always have to have a model in front of you. You can also, once you get better at seeing these things on your paper, you can imagine, well, if I put my hand in the paper and I oriented it, would it count 1, 2, 3, or would we count 1, 2, 3 that way? All right, that's where we stopped with 10 o'clock, so we'll do that now. Have a great weekend, and I will see you Monday.